In 2012, the world of particle physics witnessed a groundbreaking discovery that sent shockwaves through the scientific community and beyond. Headlines blared with titles like "Physicists Find Elusive Particle Seen as Key to the Universe" and "God Particle Found," marking one of the most significant scientific triumphs in decades. This monumental achievement was the long-awaited confirmation of the Higgs boson, a unique particle responsible for giving fundamental particles their mass. However, what may surprise many is that this particle was never directly seen or measured. The question then arises: what exactly constitutes a measurement in the world of particle physics, and how can scientists declare the discovery of a particle they can't see? This video delves into the truth about particle discoveries, shedding light on how many of the particles in the Standard Model, the foundation of particle physics, remain hidden from direct observation, yet their existence is firmly established. Let's explore the remarkable world of particle physics and how we can be certain of the existence of particles that elude direct measurement. The nature of particles. The foundation of understanding particles in particle physics lies in the Standard Model, which lists all the fundamental particles known to us. These fundamental particles are the building blocks of the universe and make up everything we can observe. However, it's important to recognize that we've never actually seen or directly measured most of these particles. According to the Standard Model, particles are not solid, tiny billiard balls, as one might imagine, but rather, they are excitations or waves in quantum fields that extend throughout spacetime. Each particle corresponds to a quantum of energy in its respective field. For instance, an electron is an excitation in the electron field with an energy equivalent to its rest mass, which is about 0.511 mega-electron volts, MeV. Creating heavy particles. If you want to create a heavy particle, like the Higgs boson, you need to add a significant amount of energy to the corresponding field. The Higgs boson, with a mass of approximately 125 giga-electron volts, GeV, requires the addition of 125 giga-electron volts of energy to the Higgs field to manifest as a particle. This is quite a high energy level, equivalent to the rest mass of about 244,000 electrons. In principle, you can achieve this by adding energy to the field, but in practice, it's challenging because the Higgs is significantly heavier than most other particles in the Standard Model. Particle decay. A fundamental concept in particle physics is that heavy particles are generally unstable and tend to decay into lighter particles over time. This is rooted in the principle that everything in the universe tends to move toward its minimum state of energy. When a particle can decay into something lighter, it will eventually do so. The heavier the particle, the faster it decays. For example, the tau particle, which is a heavier cousin of the electron, has a very short lifetime of about 2.9 by 10 to the power of -13 seconds. On the other hand, the electron is stable because it's the lightest particle of its kind, and there are no lighter particles for it to decay into. Detecting heavy particles. The challenge in detecting heavy particles like the Higgs lies in their short lifetimes and the energy levels required to create them. These particles decay almost instantly, making it nearly impossible to directly detect them. Additionally, the way particle detectors are constructed, particles that don't move, i.e., stationary within the beam, are not easily detectable since detectors are designed to pick up particles that move away from the collision point. Indirect detection. So, how do scientists manage to detect heavy particles like the Higgs if they can't be directly observed? The answer lies in the study of decay products. When particles like protons are accelerated and smashed together, a cascade of particles is produced in the process. By examining the properties and energies of these decay products, scientists can make inferences about the existence of heavy particles like the Higgs. The idea is that, if a collision event produces decay products whose combined energy matches the mass of the Higgs, it is highly likely that a Higgs particle was created during the collision. Statistical significance. Particle physics relies heavily on statistical methods to establish the existence of particles. The declaration of a particle's discovery is typically made when the results achieve a high level of statistical significance. In particle physics, this is often expressed in terms of sigma levels. For example, a discovery with 5 sigma significance is considered the gold standard. It implies that there is only a 1 in 3.5 million chance that the observed result is a statistical fluke. Higgs boson discovery. The Higgs boson, one of the most elusive particles in the Standard Model, was discovered at the Large Hadron Collider, LHC, by examining the decay products of collision events. The Higgs boson has an extremely short lifetime, and it decays into other particles almost instantaneously. Interestingly, one of the significant decay paths for the Higgs involves the production of high-energy photons. While the Higgs boson itself doesn't directly interact with massless particles like photons, it decays into heavy bottom/anti-bottom quarks, which are electrically charged. These quarks interact with photons, and the energy of the photons adds up to the mass of the Higgs. So, what scientists detect are these high-energy photons rather than the Higgs boson itself. In essence, the field of particle physics relies on indirect methods to study and discover fundamental particles. While heavy particles like the Higgs boson are never directly observed, their existence is inferred from the behavior and properties of the particles they decay into. This inference is made with a high degree of statistical confidence, based on the properties and energies of decay products. It's a testament to the power of modern physics and the complexity of particle interactions. Thank you for watching another episode of Elusive. While you are still here, don't forget to like and subscribe.